All right, in this first example, we are solving a system of linear inequalities. So notice that there are no equal signs strictly in either of these equations. Like this one is y is less than 4, but this one is y is greater than or equal to 3 halves x minus 1. So we're not looking for just one point where these two lines meet. We're actually looking for a whole area of points that make both of these inequalities true at the same time. So let's go through a really popular method for actually graphing the solution to this. So I'll start by first graphing the equation y is equal to 4, but I'm going to use a dashed line to indicate that I'm not including the line itself. So y equals 4 is just a horizontal line at 4, so I'll mark that in here kind of like this. There we go. So there is y is equal to 4. Now in red, I'm going to graph the equation y is equal to 3 halves x minus 1. So this time I'm going to use the slope-intercept to graph this line. So if the y-intercept is -1, it's right here, and the slope is 3 over 2, that means we go up 3 places and 2 places to the right. So counting from here, I get 1, 2, 3, and I get 1, 2 over. So I get the point 2 comma 2. I'll mark that here. And I'm going to have a solid line that goes through these 2 points since there's an equal sign on the original inequality. So I get this. And I can actually see that these 2 points meet here at what looks like 4 comma 4. But I'm not looking for that point. Instead, what I'm looking for is where are all the points where y is less than 4, but also y is greater than or equal to 3 halves x minus 1. So here's the way I think about it. Here's y is equal to 4. And if I'm saying y is less than this, I'm below this line. But at the same time, if this is y is equal to 3 halves x minus 1, and I'm greater than it, I want to be above the line. And I'm looking for the overlap between these two areas. And I'm going to mark that in green. But below 4, yet above 3 halves x minus 1, that's referring to this area here. I mean, technically there are 4 different places to choose from. Here, 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 and here. But only one of them can be true for this system of linear inequalities. There's another way that you could maybe make this a little bit more formal. What I'm going to do is choose a point within the area, and I'll choose a simple one, 0, comma 0. If 0, comma 0 makes both of these inequalities true at the same time, I know I actually shaded in the correct area. So let's check it out. We have y is less than 4. Does this point make this inequality true? Well, x equals 0 can't go anywhere, but 0 would go in place of y, and what do you know? It's true that y is less than 4, so great. But what about y is greater than or equal to 3 halves x minus 1? Well, I'll put 0 in place of y, I'll put 0 also in place of x, and I'll simplify this, and right, 0 is greater than or equal to -1. So like here's a good way if like you're not sure which region to look at, you can actually just choose a point within that region to see if it works. It might be worthwhile like checking a region that doesn't work to see what goes wrong. So I'll put a point, it could be anywhere, but maybe I'll choose 5 comma 0. Like this should not be in my answer, so something should go wrong if I plug it into the system of linear inequalities. So that's 5 comma 0. If I put that in place of y is less than 4, well, 0 would go in place of y, 5 doesn't go anywhere, and you end up with a true statement. So something must go wrong with the second equation. Let's check it out. I have y is greater than or equal to 3 halves x minus 1. So I'm putting 0 in place of y. I'm putting 5 in place of x. I didn't really choose an easy point to work with, but let's continue. I have 0 is greater than or equal to, that's 15 halves minus 1. I mean, I can see that this goes wrong, but maybe just to take it one step further. 15 halves is 7.5, and 7.5 minus 1 is 6.5. And whoop, that's false. That's not true. So what happened is I chose a point, it worked for one of the equations, but it just didn't work for both of them. And the fact that something went wrong means I would not want to include this point in my answer. So just to reiterate, the answer is actually this region over here, where we are below y equals 4, yet also above 3 halves x minus 1. And for the last example, same idea, just wanted to look at maybe a couple of different equations just to see how it might change things in our work. But same idea, I have two linear inequalities. I want to graph both of the lines and see what points work for both inequalities at the same time. So I'll start with x plus y is equal to 5. You know, this one's set up in a really nice way where I know 5 works for both x and y as long as the other value is 0. So we get 5 comma 0 for one point, 0 comma 5 for the other. I'll draw the line that goes between those 2 points. And here is the line x plus y is, well, equal to 5. And we'll deal with the less than later. So it's a solid line because I have an equal sign on the inequality. Okay, now for my other line, I have 2x minus y is greater than 1. I'll do a little work over here. I really want to graph this line, 2x minus y is equal to 1. I'll just make it a dashed line when I have my final graph. So I'll add y to both sides and subtract 1 from both sides. Maybe I'll write it as y is equal to 2x minus 1, so I know my slope and my y-intercept. So to graph this line, I get 0, negative 1, and the slope is 2 over 1, so it's up 2 and over 1. I actually, again, can see, that I get another point here where they intersect, but this is going to be a dashed line. Okay. So I have the setup. I just need to know which region of the xy plane I'm going to keep. So I have 4 choices. I have this place, could be one of these places over here, but only one of them is going to work. It might not be as obvious, like am I above the line or below the line, so I think what I'm going to do is just, choose some regions and see what happens. I, again, like going to maybe the simplest point, and that would be 0, 0. That would be referring to this region here. If it works, then I know this whole region must work. So let's try it out. I'm going to put 0, 0 into both equations. So for x plus y is less than or equal to 5, this is clearly true. 0 plus 0 less than or equal to 5, definitely, that is true. If I plug this into 2x minus y is greater than 1, that's not going to work. I get 2 times 0 minus 0 is greater than 1, but 0 is not greater than 1. That's false. That's no good. So 0, 0 doesn't work. That means this region cannot work. Now, if I think a little bit about what went wrong, 0, 0 worked for this line. So below this line, that seems to be good. Maybe I want to choose something that's also below this line. So I'm thinking I'm going to choose something, in this region over here. There's a lot of options. Maybe I'll choose, let's see, what would be a good choice? Maybe I'll go with 2 comma 0. I'm hoping that it works for both of my equations. Let's see what we get. For x plus y is less than or equal to 5, I can already see this is going to work because that's 2 plus 0 is less than or equal to 5, or 2 is less than or equal to 5. That's certainly true. For my second equation of 2x minus y is greater than 1, okay, putting in 2 for x and 0 for y does yield a true statement of 4 is greater than 1. So it did work for both. That means the region has to be this one here. So all the points over which I shaded have to make both inequalities true at the same time. It might take you a few guesses till you get the right answer, but you're going to eventually run out of places to check. So when going through this, try to reason it out first to make an educated guess. Don't just like pick one spot, plug in the point, and go from there. Like try to think about, should I be below or above a given line? And then if you do choose a point that doesn't work, think about which equation went wrong. This will limit down the number of places you actually do need to check. And that is it for example 2.